potential for life in the universe. While these planets themselves may not be habitable, they serve as valuable laboratory environments for studying atmospheric science and the potential for life-bearing conditions on other celestial bodies. As we continue to explore the cosmos, studying hot Jupiters can reveal much about the diversity of planetary systems and the fundamental processes that govern them. Hot Jupiters are fascinating worlds that differ dramatically in temperature compared to the gas giants in our own solar system. These exoplanets, which orbit very close to their stars, experience extreme heat, with surface temperatures soaring well above those found in our solar system's outer planets. For instance, while Jupiter itself has an average temperature hovering around -200 degrees Fahrenheit, hot Jupiters can reach scorching temperatures exceeding 2000 degrees Fahrenheit. This stark difference stems from their proximity to their host stars. Hot Jupiters orbit much closer than Mercury, the closest planet to our Sun, which means they endure intense solar radiation. Their thick atmospheres, which consist mostly of hydrogen and helium, can lead to a phenomenon known as a thermal inversion, where temperatures increase with altitude instead of decreasing, creating a hot upper atmosphere. This atmospheric reaction can generate heated winds and contribute to extraordinary weather patterns unlike anything we see on gas giants in our solar system. The temperature extremes on hot Jupiters also allow for unique atmospheric chemistry. Scientists have detected the presence of exotic molecules such as sodium and potassium, which thrive under such high temperatures. This results in the possibility of bizarre cloud formations that can contain vaporized metals, pointing to conditions on these worlds that are both alien and intriguing compared to the more familiar environments on the planets we are accustomed to, such as Saturn or Uranus. The study of hot Jupiters not only expands our understanding of planetary formation and evolution, but also stretches the boundaries of what we thought was possible in planetary atmospheres. By contrast, while our solar system hosts predominantly chilly gas giants, these distant worlds challenge our imagination and offer a glimpse into the incredible diversity of planetary systems across the universe. Hot Jupiters are a fascinating class of exoplanets, large and gaseous, orbiting very close to their parent stars. Studies of these extreme worlds have revealed that they experience significant atmospheric loss due to their intense proximity to scorching stellar radiation. This process occurs through a mechanism known as atmospheric escape, where the heat from the star energizes the gases in the atmosphere, allowing some of them to reach escape velocity and dissipate into space. The implications of this atmospheric loss extend beyond just understanding hot Jupiters themselves. As scientists scrutinize these planets, they are uncovering vital information about how atmospheres behave under extreme conditions. For instance, some studies have observed that the atmospheric composition of hot Jupiters can change dramatically over time due to this loss. This finding informs our understanding of atmospheric dynamics, and it raises important questions about the potential for habitability on smaller, Earth-like planets that may be located within the same stellar systems. Moreover, these investigations highlight a critical aspect of planetary evolution. The ability of a planet to retain its atmosphere can significantly influence its future habitability. If a planet orbits close enough to its star, like a hot Jupiter, it may rapidly lose its atmosphere, leading to a barren, inhospitable environment. In contrast, a planet further from its star may retain a thick atmosphere rich in elements essential for life. Therefore, understanding these processes on hot Jupiters not only sheds light on their own fate, but also provides a framework for evaluating the habitability of other exoplanets. Ultimately, the study of hot Jupiters serves as a reminder of the diverse and dynamic nature of planetary systems in our universe. Through these investigations, scientists are piecing together the intricate puzzle of how planets form, evolve, and ultimately address the tantalizing question of what makes a world suitable for life. This pursuit enriches our knowledge and occasionally leads to unexpected revelations about the cosmos and our place within it. A super-Earth is an intriguing category of exoplanet, defined primarily by its size and mass. These planets typically weigh more than the Earth, but less than 2 to 3 times our planet's mass. This characteristic places them in a zone where gravitational forces allow for fascinating possibilities regarding their composition and environments. While many super-Earths reside within their stars' habitable zones, meaning they exist at distances where liquid water could potentially be present, their diverse characteristics set them apart significantly from our home. Unlike Earth, which is predominantly rocky, some super-Earths could be gas giants, with thick atmospheres that might envelop their solid cores. This variety in composition poses exciting questions about the potential for different geological activities and climates. Imagine planets with vast oceans, or those carpeted with certain types of metals and minerals due to the pressures they experience in their interiors. Such differences could lead to entirely new forms of geology, and perhaps even alien ecosystems. Another defining trait of many super-Earths is their varied atmospheric compositions. Some may possess swirling clouds of gases like carbon dioxide or methane, which could create extreme greenhouse effects, leading to scorching temperatures. Conversely, others might foster conditions somewhat reminiscent of Earth's, supporting liquid water and possibly life. This begs the question, what sort of life might emerge on a planet where conditions, however similar, diverge so significantly from our own? The study of super-Earths ignites our imaginations and inspires scientists on their quest to locate planets that might host life beyond our solar system. As we fine-tune our ability to discover and analyze these distant worlds, we not only expand our understanding of planet formation and evolution, but also explore the very essence of what constitutes a habitable world. The existence of super-Earths serves as a compelling reminder that our universe is filled with possibilities, and perhaps one day we could learn more about what lies beyond our familiar planet. The discovery of water or water vapor on super-Earths, planets that are larger than Earth but smaller than gas giants, carries profound implications for our understanding of the cosmos. Water is a fundamental ingredient for life as we know it, and its presence expands the possibilities of habitability beyond our own planet. Super-Earths may be rocky potential homes, harboring conditions that could support life, prompting scientists to look closer at these intriguing worlds. Understanding the conditions necessary for water to exist is crucial. On super-Earths, the pressure and temperature can vary significantly compared to Earth. Some of these planets may sit in what is known as the habitable zone, the region around a star where conditions are just right for liquid water to exist. This zone is not fixed and changes based on the type of star and the planet's atmosphere, making the study of water on super-Earths a dynamic and exciting field of research. Moreover, finding water vapor can also indicate active geological processes. The presence of water vapor might suggest that a planet has a thick atmosphere where weather systems could develop, possibly leading to surface conditions favorable for life. Such findings stimulate not just curiosity, but also the potential for future exploration. As we seek to understand our place in the universe, super-Earths with water signify that we are not alone in our quest. These discoveries could lead to identifying other life forms and deepen our grasp of planetary formation and evolution. Ultimately, the hunt for water continues to unlock doors to questions about existence, life beyond Earth, and the myriad possibilities that lie among the stars. Super-Earths, intriguing celestial bodies that lie between the sizes of Earth and Neptune, present a fascinating arena for exploring the potential for life beyond our planet. Their greater mass implies a stronger gravitational pull. This increased gravity can significantly influence not only the planet's atmosphere, but also the physical conditions on its surface, which may affect the emergence and sustenance of life. One of the primary effects of higher gravity is the retention of a thicker atmosphere. This can lead to a more stable climate, which is essential for the development of life. A robust atmosphere can help to regulate temperature and protect any potential life forms from harmful space radiation. However, maintaining such an atmosphere over time depends on the planet's geological activity and magnetic field, both of which can be influenced by its size and gravity. Yet the increased gravity presents challenges as well. Higher gravity might limit the size and mobility of organisms. Life forms might evolve to be more compact and stronger to cope with the weight of their surroundings. On a super-Earth, creatures could be built differently, perhaps resembling the dense, stocky forms of some of Earth's deep-sea organisms, rather than the elongated creatures we see on land. Overall, while higher gravity on super-Earths can enhance the possibility of a life-supporting atmosphere, it simultaneously poses unique evolutionary pressures. Thus, The potential for life on these exoplanets remains a tantalizing question as scientists continue to investigate how life might adapt to such distinct conditions. Each new discovery adds yet another layer to our understanding of what forms life could take in the cosmos. An ocean world is a term used to describe celestial bodies that possess significant amounts of liquid water, typically beneath a thick, icy crust. These worlds, found in our own solar system and beyond, are characterized primarily by their subsurface oceans, which may be warm enough to support some form of life. The presence of water, an essential ingredient for life as we know it, makes these celestial bodies tantalizing subjects of study in the search for extraterrestrial life. One of the most well-known ocean worlds in our solar system is Europa, a moon of Jupiter. Evidence for its ocean comes from several observations, including its smooth, cracked ice surface that suggests a dynamic environment underneath. Additionally, data from spacecraft like Galileo has shown strong magnetic fields around Europa, indicating that there is a massive, salty ocean beneath its icy crust, which could be up to 100 miles deep in places. Scientists believe that interactions between this ocean and Europa's rocky seabed could create chemistry similar to that found at hydrothermal vents on Earth, where life thrives in extreme conditions. Another prime candidate is Enceladus, a moon of Saturn. This small, icy body has produced dramatic geysers that shoot water vapor and ice particles into space, suggesting that a subsurface ocean is actively venting into space. The Cassini spacecraft captured images of these plumes and analyzed their composition, revealing not only water but also organic molecules, a key building block for life. This exciting discovery suggests that Enceladus may have the right conditions for microbial life to exist. More distant ocean worlds have also piqued the interest of scientists. Exoplanets like Europa-like moons or ocean planets have been identified in the habitable zone of their stars. In these distant worlds, researchers hypothesize about the existence of oceans based not only on the presence of water in their atmospheres, but also through models of their potential geology and heat sources. The exploration of these ocean worlds raises the thrilling possibility that life could exist in environments vastly different from our own, expanding our understanding of where and how life might thrive in the universe. The discovery of a subsurface ocean on an exoplanet could significantly enhance our search for extraterrestrial life. Oceans are critical habitats for life as we know it here on Earth, and they offer a stable environment where nutrients can circulate and complex chemical reactions can occur. If an exoplanet harbors such an ocean beneath its surface, it might provide the necessary conditions for life to develop, even in environments that seem inhospitable on the surface. This idea shifts our focus from planets that merely sit comfortably within their star's habitable zone, which is often defined by surface temperatures that allow water to remain liquid, to those with subsurface water. For example, the icy moons in our own solar system, like Europa and Enceladus, have sparked intrigue because their icy crusts hide vast oceans beneath, sustaining the potential for life. Exoplanets with similar characteristics could very well hold ecosystems that we have yet to imagine. Moreover, studying the chemical signatures that may come from subsurface oceans could be an indicator of life's presence. On Earth, microbial life thrives in extreme conditions, such as deep-sea hydrothermal vents and acidic hot springs. If we detect organic compounds or certain gases in the atmosphere of distant worlds, these could suggest biological processes occurring below the surface, guiding our explorations and studies toward these tantalizingly hidden realms. By expanding our criteria to include exoplanets with subsurface oceans, we widen the net for possible habitats for life beyond our own. This opens a new chapter in astrobiology, inviting a fresh perspective on where we might find life in the universe, proving that the possibilities are as vast as the cosmos itself. The discovery of exoplanets, or planets outside our solar system, with multiple oceans, raises fascinating implications for our understanding of potential life and planetary processes. Traditionally, life as we know it depends on water, making the presence of oceans an essential factor in the search for habitable worlds. When we consider exoplanets with more than one ocean, it suggests a more complex and dynamic environment, which could provide unique habitats and ecological niches. Multiple oceans on a single planet could lead to greater diversity in terms of temperature, salinity, and chemical composition. Each ocean could develop distinct ecosystems, potentially increasing the odds of life evolving in various forms. Consider how Earth hosts a range of environments from tropical seas to frigid polar waters, each nurturing different species. On a planetary scale, the interplay between these oceans could create a rich tapestry of biological and geological interactions that are not only intriguing, but vital for the potential for diverse life. Moreover, having more than one ocean could influence the planet's climate and weather patterns. Oceanic circulation plays a critical role in regulating temperature and distributing nutrients. If an exoplanet has multiple oceans, they could interact in complex ways, affecting everything from storm patterns to the availability of essential elements for life. This kind of environmental richness might support more robust ecosystems, which in turn could contribute to the stability necessary for life to thrive over extended periods. Ultimately, the implications of discovering exoplanets with multiple oceans open up intriguing possibilities in the search for extraterrestrial life. It signifies that our understanding of habitability is evolving. As we improve our techniques for discovering and studying these distant worlds, we may find that the universe holds an unexpected variety of environments, each with its potential for life, waiting to be explored. Rogue planets are fascinating celestial bodies that roam freely through the galaxy without being tethered to any star. Unlike typical exoplanets, which orbit around stars and may be tightly bound to their cosmic companions, rogue planets have either been ejected from their original systems or formed in isolation in the vastness of space. This means they glide through the dark interstellar medium, potentially without ever receiving light or warmth from a sun. One of the most intriguing characteristics of rogue planets is their mystery. Scientists estimate that there may be more rogue planets than stars in our galaxy. They can be as varied as planets are in stellar systems. Some might be similar to Jupiter, large and gas-filled, while others could be smaller, rocky bodies resembling Earth. Without the energy of a star, these planets also experience extreme cold, making their surfaces likely frigid and inhospitable. The formation of rogue planets is a topic of ongoing research. Some may arise when a planet is gravitationally flung from its original system, perhaps due to dynamical interactions or the influence of larger bodies. Others may form in isolation, in regions where materials gather and coalesce, allowing these worlds to emerge far from any stellar influence. The existence of rogue planets challenges our understanding of planetary formation and the dynamics of cosmic systems. They open up questions about how life might arise in such extreme conditions, and they invite us to imagine how many wonders might exist beyond the light of stars, drifting through the vast expanses of our universe. Rogue planets are fascinating celestial bodies that wander through space without a host star. These planets have been ejected from their original solar systems due to various gravitational interactions. What makes them particularly intriguing is the possibility that they could harbor life in environments vastly different from those on Earth. Without the heat and light of a star, rogue planets may seem inhospitable at first glance. However, some scientists suggest that these planets could still possess internal heat, generated by geothermal activity or radioactive decay. This heat can create subsurface oceans or warm atmospheres, potentially providing a nurturing ground for life. Additionally, rogue planets might have atmospheres rich in gases like hydrogen or methane, which could support chemical processes essential for life. It's important to consider that the conditions on rogue planets can vary widely. Some might be icy worlds, shrouded in frozen gases, while others could retain enough heat to allow for liquid water beneath their surfaces. The existence of such environments suggests that rogue planets could act as islands of life, even in the vast, dark expanse of interstellar space. As our technology advances, astronomers are developing better methods to detect rogue planets and study their characteristics. The understanding of these enigmatic worlds expands, and each discovery adds to the cosmic tapestry of our universe, reminding us that life may find a way to thrive in the most unexpected places. The study of rogue planets, those wandering through space without being tethered to a star, offers unique insights into the processes of planetary formation and evolution. Unlike planets that orbit stars, rogue planets were either ejected from their original solar systems or formed in isolation. This aspect makes them invaluable to scientists seeking to understand the various pathways by which planets can come into existence. By examining rogue planets, researchers can test different theories about how planets are formed in diverse environments. For instance, rogue planets may reveal clues about the conditions present in their parent systems before their expulsion. These planets could hold remnants of their formation history, revealing the materials and processes that contributed to their development. This information could indicate the types of environments that favor the creation of planets, supporting or challenging existing models of planetary formation. Additionally, the existence of rogue planets raises intriguing questions about planetary stability and survival. The forces at play in a planet's environment can shape its evolution over time. Rogue planets often lack the warmth of a nearby star, which prompts exploration into how they maintain their atmospheres or even sustain any potential life. Understanding their characteristics allows scientists to broaden their perspective on what constitutes a habitable environment and how planets can adapt to extreme conditions. Furthermore, the discovery of rogue planets in our galaxy suggests that they might outnumber the stars themselves. This abundance challenges the traditional view of planetary systems and highlights a rich variety of planetary outcomes in the cosmos. Each rogue planet found becomes a piece of the puzzle, helping astronomers unveil the complex and dynamic history of our universe, ultimately enhancing our grasp of how planetary systems evolve throughout cosmic time. Through these wanderers, we gain a broader perspective of the universe's remarkable diversity. Technological advancements have fundamentally transformed our understanding of exoplanets, which are planets located outside our solar system. Just a few decades ago, the existence of these distant worlds was largely theoretical. Today, thanks to cutting-edge technology and innovative methods, we have confirmed thousands of exoplanets, broadening our understanding of the universe and our place within it. One of the pivotal developments in exoplanet discovery is the launch of space telescopes. Notably, the Kepler Space Telescope revolutionized this field. Operating from 2009 until its mission ended in 2018, Kepler utilized a technique called the transit method. By monitoring the brightness of stars, Kepler detected tiny dips in light that occur when a planet passes in front of its host star. This single innovation led to the discovery of over 2,500 exoplanets during its mission. Moreover, advancements in spectrometry have played a crucial role in studying the atmospheres of these far-off planets. By analyzing the light that filters through a planet's atmosphere as it transits in front of its star, scientists can determine the chemical composition of the atmosphere. This powerful method has provided key insights into the potential habitability of exoplanets, revealing the presence of elements such as water vapor, carbon dioxide, and even methane. In recent years, ground-based observatories have also embraced new techniques and larger telescopes equipped with advanced adaptive optics. This technology corrects the blurring effects of Earth's atmosphere, enabling astronomers to observe exoplanets more clearly. With these combined advancements in space and ground-based technologies, our ability to discover and study exoplanets continues to expand, uncovering new worlds and exciting possibilities for life beyond Earth. Artificial intelligence plays a transformative role in the study of exoplanets, the intriguing worlds orbiting stars beyond our solar system. With the sheer volume of data generated by telescopes and space missions, traditional methods of analysis often fall short. Artificial intelligence can sift through vast amounts of information quickly and efficiently, identifying patterns that human scientists might miss. This capability is particularly crucial when detecting tiny changes in star brightness that may indicate an exoplanet is passing in front of a star, a method known as the transit method. One way AI contributes is through the development of machine learning algorithms. These algorithms can be trained using data from known exoplanets, allowing them to recognize the unique signatures associated with planetary transits. By doing so, AI can help categorize and prioritize potential exoplanet candidates for further study, significantly speeding up the research process. The accuracy of these algorithms has improved so much that they can sometimes even uncover new planets in historical data sets that scientists had previously overlooked. Furthermore, AI is utilized in analyzing the atmospheric composition of exoplanets. By examining the light that passes through a planet's atmosphere during transits, researchers can gather clues about the elements present. Here, machine learning aids in interpreting this spectral data, identifying the chemical signatures that indicate the presence of gases such as water, carbon dioxide, or methane. This information is vital for assessing whether an exoplanet might be habitable or even host life. The integration of artificial intelligence into exoplanet research enhances our ability to process and analyze massive datasets, revealing new worlds and deepening our understanding of their characteristics. As these technologies continue to evolve, they promise to revolutionize our approach to finding and studying exoplanets, bringing us closer to answering the profound question of whether we are alone in the universe. The James Webb Space Telescope, often referred to simply as Webb, is poised to revolutionize our understanding of distant planets in ways that previous telescopes simply could not achieve. One of the remarkable features of Webb is its ability to observe the universe in infrared light. This capability allows the telescope to peer through cosmic dust and gas, which often shroud celestial objects from view. By capturing this infrared light, Webb can uncover the hidden details of distant star systems and explore the atmospheres of exoplanets, which are planets located outside of our solar system. What sets Webb apart is its unprecedented sensitivity and resolution. With its powerful instruments, it can detect the faint light from afar, enabling astronomers to study the chemical compositions of exoplanet atmospheres in detail. This insight is crucial, as understanding what these atmospheres are made of can give us clues about their potential habitability. For instance, the presence of certain gases might suggest biological processes similar to those found here on Earth, igniting our imaginations about life beyond our planet. Additionally, Webb is designed to focus on some of the most intriguing planetary systems, particularly those that resemble our own. This includes studying various stages of star and planet formation, as well as observing the evolution of planetary systems. Each observation delivered by Webb has the potential to refine our models of how planets form and develop over time, enhancing our grasp of the cosmos. The introduction of the James Webb Space Telescope represents a significant leap forward in our scientific toolkit. By revealing the atmospheric secrets of distant worlds and examining their formation and evolution closely, Webb not only enhances our understanding of these far-off planets, but also offers a broader perspective on the universe's diversity. Each discovery opens up new questions, fueling a cycle of curiosity and exploration that may reshape our view of life in the cosmos. The discovery of exoplanets has profoundly reshaped our understanding of humanity's place in the universe. Until a few decades ago, our solar system was thought to be unique, a solitary oasis of planets circling a singular star. However, astronomers have now identified thousands of exoplanets, planets orbiting stars outside our solar system. This realization has expanded our view, indicating that the universe is teeming with countless planetary systems, each possibly hosting conditions conducive to life. With over 5,000 exoplanets confirmed, our perspective shifts not just in terms of numbers, but in the diversity of these worlds. Some orbit close to their stars in scorching heat, while others lurk in the frigid reaches of space. Many lie within a star's habitable zone, where conditions might be right for liquid water, a crucial ingredient for life as we know it. These discoveries suggest that the ingredients for life may be more widespread than we previously imagined, fueling the hope that we might someday find extraterrestrial life. Moreover, the nature of these planets challenges our definitions of habitability. Some exoplanets exhibit atmospheres unlike anything on Earth, with clouds of vapor and gases that could sustain alien ecosystems. The variety of conditions observed across different exoplanets invites us to reconsider our understanding of what life can be and where it can thrive. This opens the door to the exciting possibility that life exists in forms beyond our comprehension. Ultimately, the search for exoplanets has ignited a sense of wonder about our cosmic environment. Humanity is no longer isolated in a vast, empty cosmos. Instead, we belong to a vibrant universe filled with potential neighbors, each one with a unique story and possibilities yet to be discovered. This realization encourages both humility and optimism as we reflect on our existence and the future of exploration in the cosmos. Throughout history, humanity has had a deep fascination with the stars, leading to the creation of various stories and myths that explore the possibility of life beyond our own planet. Across cultures, these tales reflect our curiosity and hope, weaving together elements of the cosmic with the possible existence of extraterrestrial beings. In ancient Mesopotamia, for example, the Sumerians believed in a pantheon of gods who came from the heavens. The Anunnaki were alleged to have descended from the stars to shape humanity and impart knowledge. This narrative not only illustrates an early connection between deities and the cosmos, but also plants the seeds for concepts that resemble the search for life on other worlds, as if granting the idea of celestial visitors a sacred status. Moving to the Americas, many indigenous cultures have their own interpretations of the stars and potential inhabitants. The Hopi tribe, for example, speaks of the Kachinas, spiritual beings who inhabit the stars and bring life to the earth. Their stories often intertwine themes of balance and harmony, suggesting that life exists in the cosmos and is inherently connected to life on Earth. Such narratives encourage a respectful view of the universe and the life forms it may harbor. As technology advanced and space exploration became a reality, these myths transformed into poignant inquiries about